Silberstein. I'm from the Technion, the Israel Institute of Technology. I'm chairing the session. And the first speaker is Lieven Eeckhout, who is going to talk about NUBA, non-uniform bandwidth GPUs. And as it's customary, you say like, those are on the market, those are the last year PhD, and he's not on market and not last year PhD. So yeah, go ahead.
Thank you, Mark, for the introduction. Yeah, so this is work done with my former PhD student, Zhao, who couldn't make it because of visa issues, and in collaboration with my collaborator, Magnus Jahre in the Norwegian University of Science and Technology. So yes, this talk is about non-uniform bandwidth architecture GPUs. Now today's GPUs are what we call uniform bandwidth architectures in the sense that the amount of bandwidth provided between the SMs and the LLC slices is uniform. So as you can see on this diagram, the LLC slices are on the memory side of the NOC. Yeah? So they are shared by all SMs, and so this is what we call a memory side UBA. And so the LLC slices cache data from their respective memory partitions for all other SMs to access. Now, the implication of this is, of course, that the SMs need to access the entire memory space through a high bandwidth crossbar. Now, a high bandwidth crossbar, no surprise, incurs high NOC power, NOC complexity, and high NOC cost. Now, to reduce the complexity of the NOC, you could put the LLC slices on the other side of the NOC. And this is actually what is being done in an SM side UBA. NVIDIA's A100 is actually implementing this. So we have the LLC slices on the SM side of the NOC, and so the LLC slices become private to an SM partition. So the SMs are organized in different partitions, and each partition has its own local private LLC. And the LLC slices cache data from all memory partitions. Yeah? So you could have multiple copies of the same cache line in different caches, and as a result, you need cache coherence support among these LLC partitions. Clearly, there is a trade-off in terms of intra-partition crossbar complexity and coherence complexity in this architecture. Now, coherence support, as we all know, is fairly complex, and it raises scalability concerns. So what we propose in this work is a non-uniform bandwidth architecture, NUBA, in which the SMs are connected to a local LLC slice and a memory partition using high bandwidth direct links. And then there's also a possibility to access remote LLC slices and memory through a low bandwidth lean NOC. And so the cache lines are cached in their local LLC slice that is local to the respective memory partition. And a key attribute is that there's no hardware coherence here. And so we really have non-uniform bandwidth in this architecture. When you're accessing a cache or a cache block that is locally cached, then you have high bandwidth. If you need to access a remote cache line, then you have much lower bandwidth. So the key assets of this architecture are high bandwidth, if you can access the local LLC partition or memory partition. And at the same time, we have reduced NOC complexity because if most of the data is local, then we become less sensitive to the NOC bandwidth, and then we can greatly reduce the complexity of this crossbar. Of course, as you can see, NUBA is quite similar to the NUMA ID from the CPU world, but the motivation is quite different. And the motivation here is really to expose and increase effective bandwidth and not so much to reduce the effective latency. Now, a key challenge here is to maximize local memory accesses for all workloads without hardware coherence. Yeah? And this is what we achieve in this talk through the use of the compiler, runtime, and hardware support. And that's what I will spend most of my time on discussing in this talk. And at the end of the day, what we achieve is higher performance and low power. So this graph is showing sort of a summary results, normalized performance as a function of the crossbar power consumption for memory side UBA, SM side UBA, and NUBA, a GPU. So there's different ways in which you can exploit this NUBA architecture. You could either use it to achieve higher performance for a given a power budget, or you could, for the same performance, you could drastically reduce the amount of power consumed in the NOC. So with this motivation, Let's talk a little bit about the NUBA challenge and how we address that, especially for sharing-intensive workloads. And then we address this by proposing a new memory page allocation policy and by using a model-driven data replication policy. And then I will go over some results and a quick conclusion. So the key challenge for NUBA is to have mostly local accesses, but without hardware coherent support. Yeah? So the key principle is that the cache lines are cached in the LLC slice local to the respective memory partition, as I mentioned before. And so we have high bandwidth access to data in a local memory partition, but if we need to access data from a remote memory partition, we bypass the local LLC and we go over the lean NOC to the other memory partition. This is actually a challenging architecture if you have sharing-intensive workloads. So what are these sharing-intensive workloads? Well, we can basically make a classification in what we call low-sharing workloads versus high-sharing workloads. So this graph is showing the percentage of pages that are accessed by a number of SMs. And so on the left-hand side, we have what we call low-sharing applications, in which most memory pages are accessed by only a single or just a few SMs. And so these types of workloads are like an ideal case for this architecture because most of the accesses will be local. And so it's actually fairly trivial where to place those memory pages in this architecture. It becomes more challenging for high sharing workloads when a large portion of memory pages is accessed by tens of SMs. Yeah? And so these are challenging workloads for this NUBA architecture. And the real question is where to place this data. And that's really where our LAB and MDR come in, and that's actually the meat of this paper. So let's first focus on memory page placement, and then I will talk more about data replication and to address the sharing. So let's first focus on the simple case. If we have a low sharing application, then memory page allocation is actually pretty simple. You do a first touch memory page allocation policy. So first touch means that you replace the memory page in the SM's local memory when an SM accesses it for the first time. So that works really well if you have a low sharing application. The memory pages actually end up in the partitions where you access the data. Yeah? Now, if you have a high sharing application, what we found was that for a first touch policy, you may end up with significantly unbalanced page distribution. And so some partitions may have more shared memory pages, and as a result, many of the accesses will be remote, and of course, you have poor performance. So the basic idea of this local and balanced page allocation policy, the intuition is to place the pages in a local memory partition while avoiding imbalance. Yeah? And so the goal really is to have high local memory bandwidth, but at the same time, we want to maximize aggregate bandwidth. Yeah? So how do we do this? Well, fairly simple idea. We do first touch, right? But then when we note that there is load imbalance, we revert to what we call least first. Yeah? In which case we allocate memory pages to the memory partition with the lowest number of pages allocated so far. Yeah? So the way we do this, we keep track of the number of memory pages allocated in each memory partition. We have this metric which we call normalized page balance, and when this NPB drops below a particular threshold, which we set to 0.9 in our experiment, we go for least first, and otherwise we go for first touch. Yeah. So this allows us to achieve the best of both worlds. We mostly allocate memory pages locally. If that turns out to lead to an imbalanced execution, we start distributing the pages across the system to achieve an overall balanced page distribution. So that was the memory page allocation part. Let's now talk about the data sharing part. Now, if you have high sharing applications, the SMs will inevitably need to access remote data. Yeah? So that leads to two problems. First, you have remote accesses over low bandwidth NOC, and second, you could lead to camping effects in front of LLC slices when different SMs access the same data around the same time. Yeah? Possible solution is to do data replication. Yeah? But then, what about cache coherence? Yeah? So the thing is, we do this only for read-only shared data within kernel boundaries, so that avoids the support needed for hardware coherence, and so that allows for parallel accesses to these shared data structures. Now, of course, when you start replicating, you will put additional pressure on cache capacity. So how do you balance the gain in terms of effective bandwidth versus the loss due to reduced cache capacity? And so this is where this MDR, model-driven data replication, comes in. We balance these two using an analytical model to decide when or not to replicate cache lines. And as I mentioned before, we rely on the compiler to identify within kernel boundaries what are the data structures that are read-only and to which we can safely do this data replication. So this analytical model is an epoch-based model. We collect a number of statistics regarding local and remote accesses, LLC, miss rate, and we try to estimate what is the impact of not replicating versus replicating on the effective LLC bandwidth, and then we go along the lines of what the model predicts. And then we need to flush the LLC on kernel boundaries because within a kernel boundary, a data structure could be read-only, but across the kernel boundaries, it could be read-write shared. Yeah. I'm not going to go into the details of the model. I refer to the paper there. So let's go to some results. So we are considering 64 SMs, 64 LLC slices organized in 32 partitions, 32 memory channels accessing 4 HBM stacks. And for the baseline results, we assume a 1.4 terabyte per second interconnection bandwidth. So in terms of performance, so NUBA leads to a significant performance improvement compared to UBA. So this slide is showing memory side UBA versus SM side UBA, and then two variants of NUBA. NUBA without the data replication, so that's the NUBA no rep, and then NUBA with both LAB and MDR. And so for the low sharing applications, NUBA, even without data replication, performs really well. But then for the high sharing applications, we actually need that data sharing feature. And the performance benefit really comes from increased effective LLC bandwidth. Yeah. As you can see in this result. And so the fundamental reason really is that NUBA turns the majority of memory accesses into local high bandwidth accesses. If we dive a little bit deeper, so in terms of the memory page placement policy, LLB, so here in this slide I'm comparing the LAB against the first touch, FT, and the round robin, RR. And for the low sharing applications, no surprise, LAB performs equally good as first touch, but then for NUBA, for the high sharing applications, LAB performs equally good as a round robin policy, and so it achieves the best of both worlds. And then if you look at data replication, which is especially important for the high sharing applications, so MDR really is able to trade off the effective bandwidth increase versus the reduction in cache capacity. So here for these workloads, it was beneficial to fully replicate those shared cache lines, and in other cases, MDR was able to detect that would be a bad decision. So we have more results in the paper regarding energy consumption, a variety of sensitivity analysis, also an evaluation with the multi-chip GPUs, basically showing that as the opportunity increases, NUBA becomes more important. Yeah. So in summary, high bandwidth demand leads to high complexity, high power NOCs in modern day UBA GPUs, and so the NUBA architecture maximizes effective LLC bandwidth while minimizing NOC complexity and power consumption, and so it's really critical for NUBA to involve the compiler and the runtime system to achieve significant performance improvements and reductions in NOC power. With that, thank you, and happy to take questions.